Soraia Pimenta. I'm a lecturer here at the Department of Mechanical Engineering at Imperial College, and I'm also a research fellow of the Royal Academy of Engineering. So my research is focused on carbon fiber composites, which are very strong, very stiff, and yet very light materials that you can typically see in high-spec applications, as for instance the most recent aircraft and also sports cars. Now, what we do in our research is to apply forces to carbon fiber composites, study how they deform and how they break, and then develop mathematical or computer models to predict what we see in reality. So our latest research has been focused on a different type of carbon fiber composite that you can see here, and the main advantage of this type of material is that it can be used in a wider range of applications. So this is cheaper, this is recyclable, and we can actually make structures which are safe, which are very stiff, very strong, and still very light.
Right, so this is the material we've been testing, which is a carbon fiber composite. So it's made up of lots of layers of material, and in each layer we have carbon fibers which are embedded in a plastic matrix. We stack it all up together, then we put it in an autoclave, which is basically like a pressure cooker, and that cures the material so it becomes one solid block, all joined together. It's very lightweight. You might know this material from expensive cars or expensive bicycles or expensive airplanes. Basically anything where people are willing to pay lots of money to have something that's very light but still strong, we use this material. Yeah, what we're doing here is we have a specimen over there which we've previously damaged by dropping a weight on it from a specified height, so we know exactly with what energy we've hit it, and now we're compressing it, we're squeezing it to see when it will break, basically, because we want to find that out, and that tells us how well this material is able to cope with being damaged in real life, and whether you have a problem or not if it gets damaged. So the top of the machine is very slowly moving down by 1 millimeter every minute, and the load is ramping up at the same time. So we are now at 40 kilonewtons of load, so that's 2 cars roughly on our specimen, which is 4 millimeters wide, and the load will keep on ramping up. If you listen carefully, occasionally we can hear some small breaks of fibers. So we've now compressed the specimen by 1.5 millimeters. There's fibers, and we're at 70 kilonewtons, so 7 tons, 1.5 elephants. Balancing on our little specimen. We're hearing more damage. As we start hearing more and more damage, there's more and more things breaking, and eventually the remaining material will not have enough strength left, and that happens.
So here we are looking at some images that the camera took during the test, and what we are doing here is to track the displacements of these speckle patterns that you can see here, so the black spots on the white background, to actually see how the specimen deformed when we were applying loads.
Yeah, so the colors basically correspond to how much deformation there was. So deep blue means it was compressed a lot, and red means it was pulled in tension. And you can see as we scroll through the images and get closer and closer to the end of the test, here around where the damage was, the deformation also gets localized, so this material is deforming much more than the rest of the specimen. And then it gets more and more intense at that location, until we have the actual failure, which happened so fast the camera didn't catch it. But we see there's a crack running all the way across the specimen like that. And you can see just before the failure we have a very strong deformation right here in the damaged location.
So once we understand how a material behaves under loads, we can try to model that behavior. And what we can see here is a component from a car, and we are actually modeling what happens to these components when we apply a load. And you can see here how the computer predicts how the structure will deform in real life. And this is extremely important because it also allows us now to see which are the regions of our structure which are most likely to fail. And for instance here you can see some red spots where the material is more loaded and therefore more likely to fail, and we can actually identify exactly what's happening here to make the structure as light as possible but still very safe. So if you want to learn more about carbon fiber composites, come to my talk in the Python of Science this year, so on the 16th of May 2018. Look forward to see you there.